From Galileo's first telescope to the mind-blowing images captured by the James Webb Space Telescope, humanity has mapped a mind-boggling amount of the cosmos. Galaxies, clusters, and light reaching us from billions of years in the past. It is incredible how much we have been able to discover. But no matter what tools we invent, there is a limit to how far we can see, the edge of the observable universe. But what if we could catch a glimpse of what's out there? Not directly, but through anomalies right here, within our observable universe. This brings us to the controversial phenomenon known as dark flow. It refers to the unexplained motion of galaxy clusters, all seemingly pulled in the same direction, towards something we can't see, something far beyond the edge of the observable universe. Could this be a clue to what lies beyond, or an error in our understanding of space itself? Let's take a closer look. To talk about the dark flow and what's beyond the observable universe, we need to start by defining what astronomers call the observable universe. In simple terms, it is everything we can detect with our telescopes, satellites, and other instruments because light, or other electromagnetic signals, has had enough time to travel from those distant reaches of space to us here on Earth. Since our universe is about 13.8 billion years old, it means that the farthest observable edges are effectively limited by the distance light could have traveled in that time. Now, there's an important nuance here. The universe has been expanding ever since the Big Bang, so while we can see galaxies whose light left them billions of years ago, those galaxies are now actually much farther away than the simple speed of light times time formula would suggest. In reality, the region we can see today extends roughly 46 billion light-years in every direction, giving us an observable diameter of about 93 billion light-years. It's a mind-boggling scale. One way we define these limits is through what's known as the cosmic microwave background, or CMB. Simply put, CMB is the oldest light we can observe, radiation left over from when our universe was just 380,000 years old. The CMB forms a kind of wall in our observations because earlier than that time, the universe was so hot and dense that photons couldn't freely travel. Within this cosmic sphere, we observe not just individual galaxies, but also clusters and superclusters of galaxies arranged in a vast cosmic web. If you've ever seen a foam-like or spiderweb-like structure in astronomy videos on YouTube, that's our best visualization of how matter clumps together on these enormous scales. Voids, filaments, sheets, and clusters create a web that suggests clues about both the initial conditions of the Big Bang and the long interplay of gravity, dark matter, and dark energy. Given these observational limits, anything lying beyond that boundary remains hidden from our direct view. Yet, it doesn't mean the universe just ends there. The cosmos could extend far beyond, potentially infinitely. The question is, if there's something massive or influential out there, could its effects extend into the region we can observe? That's exactly where the dark flow comes in. It suggests that something might be exerting a gravitational pull on the largest structures we can see, even if we can't directly witness what it is. The term dark flow was coined by astronomers trying to describe an unexpected observation, a mysterious, large-scale motion of galaxy clusters. The word dark doesn't necessarily imply it has anything to do with dark matter or dark energy directly. Instead, dark refers to the unknown nature of whatever might be causing this phenomenon. Meanwhile, flow describes this idea of a collective movement. This story begins in the late 2000s when researchers analyzing data from the Wilkinson Microwave Anisotropy Probe, or WMAP, noticed something strange. They had been measuring the so-called peculiar velocities of galaxy clusters, velocities that deviate from the overall expansion of the universe. Typically, you'd expect these deviations to be random or primarily influenced by nearby, known gravitational sources, such as superclusters. But the data suggested something else. A surprising number of clusters seemed to be moving in roughly the same direction at high speeds, as if pulled by a massive structure beyond our line of sight. Initially, this finding caused a lot of excitement. If real, it might mean we've detected a gravitational force from a region outside the observable universe, some huge overdensity of matter that's tugging on these clusters. At the same time, the claim also faced immediate skepticism. Anomalies sometimes show up in large data sets, and not all of them hold up under scrutiny. Still, the researchers behind the discovery stood by their analysis. They argued that the signals they saw were statistically significant, meaning it was less likely to be a random fluke. They dubbed this collective motion dark flow, and the name stuck. But why was this so surprising? Under the standard cosmological model, often called lambda CDM, the distribution of matter on extremely large scales should appear mostly uniform when viewed in every direction, or isotropic, and mostly the same in every region, or homogeneous. If enormous clusters of galaxies are all streaming toward one part of the sky, that could imply there's a preferred direction in the universe, and that, in turn, would challenge one of the foundational assumptions of modern cosmology, the cosmological principle that states no direction or place in the universe should be special on the grandest scales. Before we jump to conclusions, though, let's take a look at the evidence in a bit more detail. The primary tools for investigating dark flow have been instruments designed to study the cosmic microwave background, the faint afterglow of the Big Bang. One of the earliest missions to provide crucial data was NASA's WMAP satellite. Later, the Planck satellite offered even more precise measurements. To understand how these missions help detect dark flow, we need to look briefly at how peculiar velocities of galaxy clusters can show up in CMB data. When a galaxy cluster moves relative to the CMB, it produces a very subtle distortion in the CMB's temperature distribution, known as the kinematic Sunyaev-Zeldovich, or KSZ effect. Essentially, hot gas within a moving cluster can slightly upscatter CMB photons. By measuring these distortions across many clusters, astronomers can estimate the cluster's collective motion. It's a challenging process. Temperature differences amount to mere millionths of a degree, so any signals must be carefully teased out of noise. In the initial studies, scientists saw patterns that weren't random. Instead, they indicated a cohesive drift, a chunk of galaxy clusters moving in a similar direction at speeds of thousands of kilometers per second. Still, the data comes with uncertainties. Extracting the KSZ signal is notoriously difficult. You need to account for many complicating factors: local gravitational effects, instrumental noise, dust emissions in the galaxy, and more. Early on, replication efforts produced mixed results. Some teams confirmed a directional motion, while others concluded the signal was weaker than first claimed or possibly non-existent. To make matters more complex, the Planck satellite, renowned for its incredible precision, later provided data that many interpreted as not strongly supporting a coherent dark flow. The Planck team's official releases suggested that any large-scale bulk flow is consistent with standard lambda CDM expectations, without requiring a big pull from beyond the observable universe. At this point, the conversation diverged. Some researchers continued to refine techniques, insisting that dark flow could still be present if measured very carefully. Others concluded that the effect was likely an artifact or statistical quirk. This is pretty much the debate. Did we detect a genuine phenomenon, or did we see an illusion caused by the challenges of analyzing faint signals on enormous scales? Despite the criticisms, the possibility of dark flow hasn't been entirely dismissed. A few studies, even after Planck, suggested subtle signals that could support a persistent drift. The discrepancy likely arises from different data processing techniques, or from focusing on different sets of galaxy clusters. This controversy comes down to the scientific method itself. Claims must be tested, retested, and subjected to scrutiny from multiple angles. It's a process that can take years, sometimes decades, before consensus emerges. In the case of dark flow, consensus still hasn't been reached. One of the main explanations for dark flow, assuming it exists, doesn't rely on anything too wild. It suggests that just beyond the boundary of our observable universe, there might be massive structures or regions of unusually high matter density. Perhaps these regions formed from slight overdensities in the early universe that grew significantly over billions of years. Since gravity acts over vast distances, these superclusters, or supervoids in other directions, could be tugging on galaxy clusters we can see, What's important to note here is that such a scenario still fits within the broader Lambda CDM framework. It doesn't require rewriting the laws of physics. Instead, it suggests that the distribution of matter on extremely large scales might not be perfectly uniform, especially in the parts we can't observe. In other words, the principle that the universe is the same everywhere is a statistical one, and small deviations might exist in specific directions. A second idea involves refining our understanding of the initial conditions set by inflation, an extremely rapid expansion thought to have occurred fractions of a second after the Big Bang. Inflation would have amplified tiny quantum fluctuations into the seed structures of galaxies and clusters. While the standard model assumes these fluctuations are random and distributed roughly evenly, there could be larger than expected overdensities outside our immediate horizon. This would again create a slight pull that could manifest as a bulk flow. Technologically, we're pushing the boundaries of how we measure these large-scale structures. The Euclid Space Telescope, launched in July 2023, has begun its mission to map the universe's large-scale structure with unprecedented precision. Meanwhile, NASA's Nancy Grace Roman Space Telescope, set to launch in 2027, will provide even deeper galaxy surveys. By comparing these maps with CMB measurements, researchers hope to determine whether any suspicious alignment or flow pattern persists. Importantly, these possibilities remain within known physics. They don't necessarily call for, say, hidden dimensions or parallel universes. The lesson is that, if dark flow holds up, it might be explained by the same gravitational principles and cosmic history we're already familiar with, just extended to regions beyond our current observational horizon. Regardless, most cosmologists agree that the universe extends beyond our observable region, probably by a vast, potentially infinite amount. Our vantage point is limited by how quickly light can travel, but space doesn't simply stop at the horizon. It continues, possibly filled with galaxies and structures just as in our visible patch, or it might have regions of slightly different densities. When anomalies like dark flow pop up, they reinforce that the portion of the universe we see may not be representative of the entire cosmos. It's a bit like living on a small island, seeing only the waters around you, and suddenly finding evidence that there's another landmass just beyond the horizon. You don't have to assume something magical is going on, just that your line of sight is incomplete. Dark flow is one of the most interesting mysteries in modern astronomy. Whether it turns out to be a real pull from something beyond what we can see, or just an error in how we interpret the data, it forces us to think bigger about the universe. It suggests that the vast part of the universe we can observe might only be a tiny piece of an even larger landscape, where unseen forces still affect what we detect today. With upcoming missions, the question of dark flow will remain important. We might confirm that our current models of the universe are correct, or we could find evidence of massive structures beyond our view causing this large-scale movement. Either way, the search for answers about dark flow highlights a key truth about astronomy. Our understanding of the cosmos is never finished. By continuing to look deeper, whether with better tools or new ideas, we move closer to solving the biggest mysteries of the universe. If you enjoyed learning about dark flow, don't forget to like this video, subscribe to Lucid Space, and press the notification bell so you never miss new videos. Thank you for watching, and see you next time.